Now next topic is identity function. It means let f be a function whose domain is A, codomain is same. It is from A to A. F from A to A defined by fx equal to x. For every x belonging to A, function keeps element unchanged. So this function, it is said to be, then f is said to be an identity function on set A, and here f is denoted as, in short, f is denoted as identity function on A. This is the symbol, identity function on A. It means this function has domain A, codomain A. It keeps element unchanged. If I take a function g whose domain is B, codomain is B, and for every x belonging to B, if y is in B, then gy equal to y. For every element y from B, when on y g works, it keeps element unchanged. G of y is y, like f of x is x. Similarly, g of y is y. Here x comes from A. X comes from A. Here y comes from B. So g of y is y. Element remains unchanged. So this is, then g is said to be identity function on B. If we take f from R to R, fx equal to x, so this is said to be identity function on R. So it is an identity function on R. So this is the identity function on R. It is denoted as IR. So it is f equal to IR. So this is the notation for this function f. So now this function will be used in next definition, and the word is invertible function. Invertible function. Say, to understand this definition, I am taking here a diagram that, suppose here f is a function from A to B. Here I am taking function f in which domain contains x1, x2, x3. Codomain contains y1, y2, y3. This is domain, this is codomain. Image of x1 is suppose y1, image of x2 is y3, image of x3 is y2. So this function is 1 1 and onto. It is 1 1 and onto. Now I show here inverse of this function. So here when we show inverse of any relation, this relation is a function. Now we are putting its inverse relation. So that means from B to A, this is B, this is A, B to A. B is y1, y2, y3, A is x1, x2, x3. Now if you observe this picture from back side, if you observe this from back side, then set B will be on left of you, B to A. So you will observe picture in which element y1 is associated with x1, y1 is associated with x1, y2 is associated with x3, y2 is with x3, and y3 is with y2 is with x3, y2 is with x3, and y3 is with x2, y3 is with x3, x2. So this is inverse relation. Now see, is it a function? So to check whether this relation f inverse, is it a function? So what we check? Every element of first set must be associated uniquely. Every element is associated and uniquely. y1 is associated with only x1, y2 is with only x3. No element of this first set is associated with more than one element. So this is relation as well as it is also a function. So this is a function, it is a function. This was 1 1 and on 2 function, so its inverse is also a function, because its inverse will also be 1 1 and on 2. Now here I take one more diagram. Suppose here if we take A, this is B, here x1, x2, x3, y1, y2, y3. Then x1 is associated with y1, x2 is associated with y2, x3 is associated with y2. This is neither 1 1 nor on 2. This function is neither 1 1 nor on 2. It is many 1, and because y3 is not image of any element belonging to domain, this is not on 2. So this function is neither 1 1 nor on 2. Let me say this function is g. It's a function. This is a function, but it is neither 1 1 nor on 2. Now if we think about its inverse relation, now inverse of this diagram will be, so here I am putting inverse. Here this is set B, this is set A. y1 is associated with x1, y1 with x1, y2 is associated with x2 and x3, x2 as well as x3, and y3 is not associated with anyone. So now observe this picture. Is this relation, it is inverse of this relation, it is G inverse. Is this relation a function? So answer is no, because every element of a first set is not associated, as well as this is not related uniquely. y2 has two images. Because this element has two images, it is not a function. This is also not associated with any element, so this is not a function. So it's a relation but not a function. So G inverse is not a function. This is not a function. So remember, if a function is 1 1 and onto both, then its inverse exists. This is the practical meaning of inverse function. Now, definition of invertible function in different way. This was the practical meaning of invertible function. This function is invertible. This function is not invertible because it was neither 1 1 nor 1 2. Any function is invertible if it is 1 1 and onto both. Both is required. If function is 1 1 and onto both, then and only then its inverse exists. Otherwise, no doubt, it is a relation but not function. Say here, this is a relation. G inverse is a relation from set B to set A, but it is not a function. So inverse relation is function if given function is 1 1 and onto, then its inverse exists. And when any function its inverse exists, then if we take a composition of these functions, then composition gives always identity function. Composition of f and g, composition of f and its inverse, or f inverse and f, composition gives function as this composition gives identity function. See, what is the meaning of the statement just I have spoken, putting here? A function f from A to B is said to be an invertible function. Function is said to be an invertible function if there exists a function g from B to A such that composition of G with F, G O F, this composition and this composition both are identity functions. GOF is identity function on A. Say domain of F, we keep here, domain of F is A, so put here A. Domain of G is B, so this is identity function on B. For any given function f, if we can find a new function B to A such that composition of f and g, both compositions, GOF is identity function on A, FOG is identity function on B, then this f is said to be invertible function. So remember these words, a function f from A to B is said to be invertible if there exists g from B to A such that GOF is identity function on A and FOG is identity function on B. And here g is denoted as f inverse. So this is g if this is f. So if you take composition of f and g, FOG or GOF, both compositions will be identity function. Both will be identity. So this is the definition of invertible function. G is said to be inverse function of f. So here f is from A to B Now G I replace by this symbol F inverse. F is from A to B, and if its inverse is F inverse, I have taken here F inverse from B to A. Then here I am putting F inverse. F inverse OF is identity function on A, and FO F inverse is identity function on B. So taking composition of any function with inverse function, we get identity function. Identity function on which set? So put here domain of a first function. First function is F. So here we keep domain of F. Here first function of is F inverse. Its domain is B. If we take inverse of inverse, then we get function itself. Inverse of inverse is function itself. If we take composition of F and G, that is G O F, and inverse of G O F, it will be equal to F inverse O G inverse. Inverse of F O G is F inverse O G inverse. So this was about invertible function. And most important statement, that function is 1 1 and onto if function is 1 1 and onto if and only if F inverse exists. If function is 1 1 and onto, then and only then F inverse exists. If F inverse exists, that means function will be 1 1 and onto. So this was the definition of invertible function. Now state whether following functions have inverse or not. If inverse exists, we shall find inverse. See, look the first function. Here domain contains 1, 2, 3, 4. Codomain contains only 10. Image of 1 is 10, image of 2 is 10, image of 3 is 10, image of 4 is 10. You can see that function is many 1. It is not 1 1. See here, 1 is not equal to 2, but under F, image of 1 is 10, image of 2 is also 10. So F of 1 is 10, F of 2 is also 10. x1 not equal to x2, but f of x1 equal to f of x2. If we can show this statement for at least one pair of numbers, then it's sufficient to say that function is not 1 1. Function is not 1 1, then inverse does not exist. See, function must be 1 1 and onto both. But here function is not 1 1, so no question of checking onto-ness. Here story is finished. Its inverse does not exist. And if you want to check onto-ness, then look here. Codomain is singleton set containing 10, and range is also singleton set containing this number 10. Range and codomain are same, so this is onto. Here range is containing 10, set of all images, and same set is codomain. it is codomain. So range equal to codomain, so this function is onto. But because it is not 1 1, therefore inverse does not exist. So F inverse does not exist. For existence of inverse, function must be 1 1 and onto both. Now here we try to understand this function by diagram. This is set containing 2, 3, 4, 5 domain. Now here I am putting codomain 7, 9, 11, 13. Image of 2 is 7. Image of 2 is 7. Image of 3 is 9. Image of 3 is 9. Image of 4 is 11. Image of 5 is 13. Under H. And here it is clear. If you select any two elements x1 and x2, distinct elements, their images are also distinct. For every x1 x2 belonging to domain, for every x1 x2 belonging to domain, taking any x1 x2 belonging to domain, x1 not equal to x2 implies fx1 not equal to fx2. It is clear. These are distinct, outputs are distinct. These are distinct, outputs are distinct. Select any x1 x2, their images are also distinct. So this function is 1 1. What is its range? Range is set of outputs. 7 is image, 9 is image, 11 is image, 13 is also image. So set of images 7, 9, 11, 13. And same is codomain. Codomain is also 7, 9, 11, 13. So range is equal to codomain. Therefore function is onto. So this function is 1 1 and onto. Function is 1 1 and onto both. And if function is 1 1 and onto both, then its inverse exists. And its inverse is, say here, sorry, notation for function is h. So I should keep here h. H is 1 1. H is onto. So H is 1 1 and onto. So H inverse exists. So H inverse will be, therefore, now showing function H inverse, therefore H inverse will be from, H is from A to B, so H inverse will be from B to A. It is from B to A, 7, 9, 11, 13 to A, 2, 3, 4, 5. So H inverse will be from B to A. H inverse defined by H inverse equal to, so say this will be reversed. In H inverse what happens? Image of 7 is 2. Image of 7 is 2. Image of 9 will be 3. 4, 11. It will be converted into 11, 4. 5, 13. It will be converted into 13, 5. So if AB belongs to H, then BA belongs to H inverse. So this is inverse of given function. If function is 1 1 and onto both, then its inverse exists. Now in this question, say given function is G, domain is 1, 2, 3, 4, codomain is 10, 11, 12, 13, 14. Image of 1 is 10, image of 2 is 11, image of 3 is 12, image of 4 is 14. You can see that here by function g, distinct input, outputs are distinct. Distinct input, outputs are distinct. So as discussed in this question, for every x1, x2 belonging to domain x1 not equal to x2 implies g of x1 not equal to g of x2. So here g is 1 function. Now we check ontoness. For ontoness, check range. So here range of function g. So range is set of images. So range contains 10, 11, 12. See, range doesn't contain 13. 13 is in codomain but not in range because it is not image of anyone. So 14. So range does not include 13. While codomain contains 13, so this range is not equal to codomain. And if range is not equal to codomain, so this function g is not onto. It is 1 but not onto. For existence of its inverse, g must be both 1 and onto. But because it is not onto, therefore g inverse does not exist. If function is 1 and onto both, then inverse exists. See here, a diagram for this function can also be shown by this way, that here, see H inverse, showing diagram for H inverse. Domain of H inverse is 7, 9, 11, 13. Codomain is 2, 3, 4, 5. What H inverse does? Image of 7 is 2. Image of 3 is 9. Image of, sorry, I did here mistake. 9, 3. Here 9, 3. This was 3, 9. So this should be 9, 3. This is 4, 11. This should be 11, 4. 5, 13. This should be 13, 5. So image of 9 is 3. Image of 11 is 4. Image of 13 is 5. So this is H inverse. So Venn diagram of this function. So this is the meaning of inverse function. So keep remember very important property. If function is 1 and onto both, then its inverse exists. Say question is, consider function from R to R given by fx equal to 4x plus 3. Show that function is invertible. Find inverse of f. Say we discussed a definition that for given function f from a to b, if we can find a new function g from b to a such that composition of g with f from either sides, GOF and FOG. GOF is identity function on A and FOG is identity function on B. If we can find g satisfying these two conditions, then f is said to be invertible function. And if f is invertible function, if function is invertible, then from y equal to fx, value of x, it will be equal to f inverse y. This is the method to find inverse function. If function is invertible, then from y equal to fx, whatever we get value of x, value of x will be f inverse of y. First of all, we check here first part. First part is show that function is invertible. So application of this definition. Here a function is given r to r. Fx is 4x plus 3. Here f is from r to r. Fx is 4x plus 3. Function is from r to r. Now we are finding a new function from b to a. That is, here it was r to r, so g will be also from r to r, satisfying this condition. So what is the procedure to find g? The method is, we suppose that y is image of x, where x comes from domain. This x comes from domain. For x belonging to R, y equal to fx. So beginning from y equal to fx, we put value of fx. So fx is 4x plus 3. Then get value of x. So x is y minus 3 by 4. Say this is equation 1. From y equal to fx, get value of x. Now we define new function g. Method is, f is from a to b. Say here g from b to a. Because codomain and domain are same, so here it remains same. Here for g, we are going to use variable y. So g of y, for f we used x, for g we are using y. So g of y is, take this value, g of y, put here. This is the method. G of y is y minus 3 by 4. So a function is created. We have found a function, but we need to check both conditions, that composition of g and f. This is g, this is f. So we want to check a composition of g and f. Composition of both. Are these compositions identity function? So let me check composition. Now first of all, g of f. G is from r to r, f is from r to r, so g of f will be also from r to r. And for all x belonging to R, g of f of x will be equal to g of fx. G of fx, so now here I will put fx. G of fx, this will come here. So same number it will be here. So g of fx is fx minus 3 by 4. So it is fx minus 3 by 4. G of fx is fx minus 3 by 4. Fx minus 3 by 4. Now value of fx. What is fx? Fx is 4x plus 3 minus 3 upon 4. So this is 3 cancelled, 4x by 4. So it is x. So what is proved here? GOF of x is x. Thus GOF, it is from R to R. GOF of x, GOF of x equal to x. If any function has domain and codomain same, and if it keeps element unchanged, then it is said to be identity function. See, I explained definition of identity function, that f is from a to a, fx equal to x. See, domain and codomain same, function keeps element unchanged. This is identity function on set A. Now similar pattern is here. See, f is from a to a, fx is x. Consider this as f from a to a, fx is x. Therefore f is identity function on a. So this condition is derived. This is derived. Now we find composition of f and g from other side, that is we find FOG. Now this was procedure for FOG. Now this was procedure for GOF. Now procedure is from FOG. FOG will be from, say here, domain of G, codomain of F. But here both are R to R, here this is R to R, so this will be also R to R. Now for all y belonging to R, in machine FOG I am putting y. FOG works on y. So FOG of y is f of gy. F of gy. That is, now f of gy. So put here gy. F of gy is 4 into gy plus 3. Whatever you keep here, same number keep here. Here I am putting gy, so put here gy. So f of gy is 4 gy plus 3. So 4 into gy plus 3. Then put value of gy. 4 into gy. Gy here we have defined y minus 3 by 4 plus 3. This is cancelled. So y minus 3 plus 3. So this is y. So FOG of y is y. This function also keeps element unchanged. Therefore FOG, it will be also from R to R. FOG is from R to R. FOG of y is equal to y. FOG of y is y. So this function has also domain and codomain same, and whatever is input same is output. It keeps element unchanged. So this is identity function. Therefore this function is identity function on R. So say this is GOF and this is FOG. Both conditions are satisfied, condition 1 and condition 2. So first of all, we have defined a function g. This function is satisfying both conditions, and if we can find g satisfying these conditions, then function is invertible. So from 1 and 2, it is proved that we can find g satisfying both conditions. So from 1 and 2 it is proved that there exists g R to R gy equal to y minus 3 by 4 such that GOF is identity function on A and FOG is identity function on B. So for given function f, there exists a new function g. From 1 and 2 it is clear that for given function f, there exists a function g satisfying these conditions. Therefore f is invertible. Function is invertible. Function is invertible, so this part is proved. Now we want to find inverse. Now see, if function is invertible, here discussed, if function is invertible, then y equal to fx double implies x equal to f inverse y. Also keep remember this very important note. So here this function is invertible. Function is invertible, therefore y equal to fx double implies x equal to f inverse y. That is, see, what is value of x? Here already we have found x. Y equal to fx. From y equal to fx, this is value of x. So there in that equation I am putting this value of x. What is x? Y minus 3 by 4. So I am putting here y minus 3 by 4. It is from equation 1. Thus f inverse is f from R to R. So f inverse will be from R to R. F is from A to B. So f inverse will be from B to A. But here because A and B are same, so in f inverse also it remains same. And this is formula for f inverse. F inverse of y equal to y minus 3 by 4. In short, this function g is itself f inverse. F inverse y is y minus 3 by 4. So this is the method to find inverse function, or we can also say in this definition it was discussed that this function g is said to be inverse function. So instead of these statements, we can also end this answer by this way. So here g is inverse of f. G is inverse of f, therefore f inverse is from, now replace g by f inverse. F inverse of y is equal to y minus 3 by 4. Only one line. Replace g by f inverse if g is satisfying this condition. This is the method to find inverse and to show function is invertible. If fx is 4x plus 3 upon 6x minus 4, x not equal to 2 by 3, so that f of x equal to x for all x not equal to 2 by 3. Say, first of all, we prove this first part. Here fx is 4x plus 3 upon 6x minus 4, x not equal to 2 by 3. Domain does not include 2 by 3, because putting here 2 by 3, this becomes 0. So function is not defined at 2 by 3. Now we find f of x. So for all x not equal to 2 by 3, that means for all x except 2 by 3, x is any real except 2 by 3, f of x, composition of function with itself, f of x is equal to f of fx. Now f of fx, that means this value I am putting here, f of fx. So going to put here fx. Whatever we keep here, same value we should keep here. So f of fx means f of fx is 4 times fx plus 3 upon 6 times fx minus 4. X is replaced by fx. Now we put value of fx. So 4 into, now fx is 4x plus 3 upon 6x minus 4 plus 3 upon 6 into 4x plus 3 upon 6x minus 4 minus 4. Now simplifying this, 4 into 4, 16x plus 12 plus 3 into 6, 18x minus 12. LCM will be cancelled. 6 into 4, 24x plus 18 minus 24x minus 16. Here this will be cancelled. 12 will be cancelled. So 16, this will be, 6x minus 4 into minus 4. So minus 24 plus 16, this will be plus 16. So it is 34x. It is equal to 34x upon 18 plus 16, 34. So it is x. So what is proved? F of x is equal to x for all x belonging to real numbers except 2 by 3. This is identity function. F of x equal to x is identity function. So f any function keeps elements unchanged on any set, then it is said to be identity function on that set. So on this set, this is identity function on, if this is A, so set A, identity function on A. Now see, we discussed definition that when GOF is identity function on A, FOG is identity function on B, then G is said to be inverse of F. Now look here, we have found composition of function itself. So now here you think here F, FOF, FOF. Think about F in place of G. So what we have derived here, FOF is identity function on whatever is set on which function defined. So FOF is identity function, that means indirectly these conditions, both conditions are satisfied, that FOG is identity function, GOF is identity function. So in this case, when this happens, what we say, G is F inverse. Now G is replaced by F inverse, sorry, G is replaced by F. So here replace G by F. So what is it now? F inverse is F. Therefore, F inverse is equal to F. F inverse is F. Therefore, F inverse of X equal to Fx. Or we can say F inverse of Y equal to Fy. So therefore, F inverse of X is, what is Fx? Fx is 4x plus 3 upon 6x minus 4. So this is F inverse. So whenever you prove composition of any function with itself identity function, then its inverse and function itself both will be same. So that function from closed interval -1 to 1, this is domain, codomain R, given by fx equal to x plus 2, it is 1 1. So first part of this question, here f is from -1 1 to R, fx is x upon x plus 2. To show that function is 1 1, we take x1 x2 belonging to domain. So for all x1 x2 belonging to domain, x1 x2 belonging to domain, beginning from fx1 equal to fx2, we are going to show x1 equal to x2. Whenever we want to prove function 1 1, and if it is 1 1, then beginning from fx1 equal to fx2, we show x1 equal to x2. So fx1 equal to fx2. Now fx1 is x1 upon x1 plus 2 equal to f of x2 is x2 upon x2 plus 2. Now simplifying this, x1 x2 plus 2x1 equal to x1 x2 plus 2x2. This is cancelled. So 2x1 equal to 2x2. So x1 equal to x2. So what is proved? Therefore, fx1 equal to fx2 implies x1 equal to x2. So this function, given function is 1 1 function. This was first part of answer. Now we want inverse of this function. For inverse of function f from -1 to, for inverse of f from -1 comma 1 to range of R. To find inverse of this function, we have to find a new function g from b to a. If this is a to b, we have to find g from b to a, such that g of f is identity function on a and f of g is identity function on b. If g satisfies these both conditions, then g is inverse of f. So we have to define g. Now how to define g? That we discussed in previous question. That to define g, method is for any y from this set, for y, any y belonging to range of f, we suppose that y is image of x. Y is from range of f, means a codomain whose inverse we want to find. We want to find inverse of this function whose domain is range of f. So for any y from this set, it means y is image, and if y is image, because it is in range, it is image of someone. So suppose y is image of fx. So from this equation, now here I am putting fx. Fx is x upon x plus 2. From this we find value of x. So xy plus 2y is x. That is, now x minus xy is 2y. We want x in terms of y. So x common, 1 minus y is 2y. So x is 2y upon 1 minus y. Let me say this is equation 1. Whenever we want to define g, to find f inverse, when we want to define g, what is the procedure? Begin from y equal to fx. Y is image of some x. Put here formula for fx, get value of x in terms of y. And now, observing this expression, we are going to define y. So define, now I am defining new function g. So define g is from, we want inverse of this function a to b. So define g from b to a. G from range f2 minus 1 to 1. So g from b to a, g of y, take this value of x for g of y. So g of y is 2y upon 1 minus y. F is from a to b, say here g from b to a, and g of y is value of x. So now we are having g, we are given f. Now we are checking both compositions, f and fog and gof. So for which we find gof. Now gof, so how to put domain and codomain? Here we put domain of a first function. What is domain of f? Domain of f is minus 1 to 1. And here we keep codomain of g, second function. Codomain of g is minus 1 to 1. domain of first function, codomain of second function. That will be domain and codomain of that composite function. So this composite function, it will work for elements of this set. So for all x belonging to -1 to 1, when g of f works on x, in this machine I am putting element from domain. G of f of x is equal to g of fx. G of fx. Now this fx I am putting here. G of fx. Whatever I keep here, same value I should keep here. So g of fx is 2 times fx upon 1 minus fx. G of fx is 2 times fx. 2 times fx upon 1 minus fx. Now I substitute value of fx. What is fx? Fx is x upon x plus 2. Here x upon x plus 2. So it is equal to here 2x upon x plus 2 minus x. X cancelled. 2x upon 2 is x. So what is proved here? Therefore g of f, it is from -1, 1 to -1, 1, g of f of x equal to x. G of f from -1, 1 to -1, 1, g of f of x equal to x. Therefore this is identity function. In this machine, if you keep x, it remains unchanged. So this is identity function. G of f is identity function on this set, close interval -1 to 1. So this is, let me say, it is result 2. Now we find FOG. FOG. This was for G of f. We have shown that G of f is identity function on domain of f. Now we are going to show that FOG is identity function on B. Identity function on B, that means a domain of G. So FOG. So here we keep domain and codomain. So domain of first function. What is domain of first function? Range f. Here I should keep range f. And codomain. Codomain of this composition should be equal to codomain of second function. What is codomain of second function? This is codomain. So range f. See, look here, we are finding inverse of this function. So consider this domain, consider this codomain. So this machine will work on all elements of this set. So for all y belonging to this set, when FOG works on y, by definition it is f of gy. Now f of gy, so I am putting here gy. F of gy is gy upon gy plus 2. F of gy is gy upon gy plus 2. So it is gy upon gy plus 2. Now g of y, it is 2y upon 1 minus y. 2y upon 1 minus y. Here 2y upon 1 minus y plus 2. So this is 2y upon 2y plus 2 minus 2y. This is cancel. It is y. So what is proved here? Therefore, FOG is from range of f to range of f. FOG of y equal to y. FOG is from B to B. FOG of y equal to y. So FOG is identity function on B. Therefore, FOG is identity function on this set range f. This is result 3. It is like G of f is identity function on A. FOG is identity function on B. So both conditions are satisfied for this function G. So f is invertible. So from 2 and 3 we can say that f is invertible. Now I need space to end this answer. So see again, here for a given function, for this function we have found G from B to A. This was f from A to B. We have found G from B to A such that this is found such that G of f is identity function on A and FOG is identity function on B. Therefore f is invertible. So from 2 and 3 it is proved that f is invertible and inverse of f is G itself. Therefore, now here I replace f inverse because G is itself f inverse by condition. That function G satisfying both condition is said to be inverse. So replacing G by f inverse. So f inverse is from range f to minus 1 to 1 defined by f inverse of y equal to 2y upon 1 minus y. So this is required inverse.